This question came in 2017 for 2 marks in set 1 for easy gate. Let's look at the question. The dependence of drift velocity of electrons on electric field in a semiconductor is shown below. So that's the figure here. It shows the drift velocity to electric field dependence. Okay. The semiconductor has a uniform electron concentration of n is equal to 1 times 10 power 16 per centimeter cube. And electron charge, standard value 1.6 times 10 power minus 19 coulomb. If a bias of 5 volt, a potential of 5 volt is applied across a 1 micrometer region of the semiconductor, the resulting current density in this region in kiloamperes per centimeter square is dash. So let's find out. In order to find the current density in this region, okay, first of all, let's see which type of semiconductor it is. They have given n is this, so it's a n-type semiconductor. If n is 10 power 16, p would be approximately to the order of 10 power 4, okay, in silicon. So n is given, which is 1 times 10 power 16 per centimeter cube, and to find the current density, J n drift, which is equal to Q n mu n times E bar. That's what we know. But in this case, the mu n is not given. Okay. Hence, we directly use the drift velocity, which is nothing but mu n times electric field. Okay. So we write this Q n times the drift velocity of electron. Now, in order to find the drift velocity of electron, it actually depends on electric field. So we need electric field anyways. So to find electric field, the potential is given. Electric field is given by the potential divided by the distance over which it is applied. So it is 5 volts per 1 micrometer. Now let's convert this into volt per centimeter, because this graph is according to that. So this can be written as 5 times 10 power 4 per centimeter, because this is 10 power minus 6, 10 power minus 4 cent above becomes 10 power 4, and 10 power minus 2 meters is centimeters. So we have 5 times 10 power 4 volt per centimeter. So if we look at this graph, if this is the range 0 to 5 times 10 power 5, 5 times 10 power 4 would come somewhere here, okay, which means we fall in this linear region. So in order to find the drift velocity, we need to find, depending on the slope. So I am taking, if the drift velocity for 5 times 10 power 5 electric field, volt per centimeter electric field, so 10 power 7 velocity, centimeters per second for a 5 times 10 power 5 electric field, then what should be the velocity for an electric field of 5 times 10 power 4? So let's find this out. So x can be written as 10 power 7 times 5 times 10 power 4 divided by 5 times 10 power 5. So this is 10 power, we can say 6. 5 cancel, 4 becomes 1, 1 it becomes 10 power 6. Now the drift velocity is 10 power 6 centimeters per second. Now let's find what is Jn drift. Now Jn drift would become Q times n times the drift velocity, which is 10 power 6 centimeters per second. Now let's substitute the electron charge, 1.6 times 10 power minus 19 coulombs, and n is 1 times 10 power 16 per centimeter cube times 10 power 6 centimeters per second. It becomes centimeter square. Now we can write this as 1.6, okay, times 10 power minus 19 and 16 we have. When we take 16 to this, it becomes minus 3, and minus 3 and plus 6. If I take out minus 3, it becomes plus 3. So I can say 1.6 times 10 power 3. Now I have coulombs per second per centimeter square. So coulombs per second is amperes per centimeter square. Now they have asked that current density in this region in kiloampere per centimeter square. So we can write this as 1.6. 10 power 3 is kilo, so kiloamperes per centimeter square. This is the Jn drift. In fact, the current density that is being asked, we can write Jn drift plus Jp drift, but the carrier concentration of holes will be very small, hence we didn't take the Jp drift. So the entire J drift would have been equal to Jn drift plus Jp drift, because this component would be very small, so hence we actually took in n-type semiconductor only this component. Hence that's why J drift is equal to Jn drift. So the answer is 1.6.